You guys are hardcore. And you want to know about deep learning and TensorFlow this morning?
It's running off of here.
Amazing. All right, sorry about that. OK, we're good to go. So congratulations to everybody who went to the party last night and still has the stamina to go through this session this morning. My name is Julian. I'm a tech evangelist with AWS, and I focus on AI and machine learning. And I guess to close reInvent 2018 in style, we have a hardcore session for you this morning. I will be joined by Kevin and Andrew from Advanced Microgrid Solutions. And I haven't seen all reInvent decks, but I think this is probably the most hardcore one you'll see on deep learning this week. So sorry if you have a bit of a headache. You still have time to grab a coffee. And hopefully we're going to blow your mind this morning. So who's using SageMaker today already? Who has looked at it? OK, all right, thanks. So we'll go through a few SageMaker slides to make sure everybody in the room understand what SageMaker is and how it helps you solve your machine learning problems. We'll talk about TensorFlow for a little bit as well. And then I'll hand it over to Kevin and Andrew, who will explain the use case and the deep learning model that they built to forecast energy prices in real time. And they went extremely far. You'll see. And then I'll come back for a few minutes, share some resources, and then I guess we can go back home and enjoy the rest of the weekend and try to recover from this crazy week, right? So a few words about SageMaker. So SageMaker was launched at reInvent last year, and we announced tons of new features this year. So if you're using SageMaker today, make sure you catch up on all those additional services and features around SageMaker. But the basic reason why SageMaker was built is because customers came to us saying, machine learning is too difficult. It takes too much time to get from the business question all the way to answering that question with a model in production. There are so many walls we need to blast through, from choosing an algo to training on dedicated infrastructure to deploying and doing that all over again with a different model, et cetera, et cetera. So to make this process faster, simpler, and just generally accessible to any developer, no matter what their experience level in machine learning is, we built SageMaker. So SageMaker is a collection of modules, so to speak. Everything is driven by a Python SDK. It's called the SageMaker SDK. You can find it on GitHub. And what this SDK does is it's going to help you orchestrate. It's going to help you drive your machine learning process. So starting from experimentation, okay, which is always the first thing you want to do. Explore your data, do some pre-processing, some visualization, maybe some basic feature engineering, trying to figure out what that data is and how you can start working with it. So to make that simple, we provide fully managed instances called notebook instances. And these are EC2 instances that come pre-installed with Jupyter notebooks, all the sample notebooks that we've written, plus, of course, all the deep learning libraries that you need. So TensorFlow and everything else is already installed. You have the NVIDIA drivers pre-installed, the CUDA environment pre-installed if you want to use GPU processing, et cetera. So in a nutshell, it's an off-the-shelf dev environment for machine learning engineers and data scientists. And then we also provide a collection of built-in algorithms. And these are machine learning and deep learning algorithms that have been written by Amazon and AWS. And they're being used as well by Amazon and AWS. So you can expect them to scale. And they're just ready to go, right? So just select one of those algos, set some parameters, point at your data in Amazon S3, and train. So literally, you do not write a single line of machine learning code, okay? And today we have 17 algos going from typical problems like linear regression, clustering, PCA, et cetera, all the way to advanced stuff like time series and anomaly detection, etc. Okay, you can see the full list on our website. We also provide built-in environments for popular deep learning libraries like TensorFlow and Chainer and MXNet and PyTorch. And you can literally bring anything else, okay? So if you use another library or if you have your custom code for training, no problem, okay? You can just build everything into a Docker container and you can use it on SageMaker to train and predict, okay? Then once you're happy, once you have figured out which algo you should use to solve that problem, you can train literally with one API call on SageMaker, or one click if you're a console person. But I'm guessing we're mostly API persons here. So one API call, fire up a training cluster. Distributed training is available out of the box. Okay, so zero setup. So fire up that training cluster, fully managed by SageMaker, zero server to manage on your side. SageMaker will train a model using the algo you selected, using the data you put in S3. And once the model is available, it gets saved back to S3, and the training instances are terminated. Okay, so you stop paying. You never overpay for training with SageMaker. You can also automatically tune the parameters for the training job. It's called automatic model tuning or hyperparameter optimization. We'll get back to that. And it's a clever way, it's a machine learning way to figure out the optimal set of parameters for your training job. Okay, so no guessing around, using machine learning to optimize machine learning, right? I like that. And then once you're happy with the accuracy of your model, you can deploy it. And again, it's one API call to deploy to a fleet of web servers serving HTTPS-based predictions. Auto-scaling, if you'd like that, in a similar fashion as EC2 auto-scaling. Or if you don't care for HTTP predictions, you can also do batch transforms, okay? So you can grab data from S3, batch predict it, and get your predictions back from S3 as well, okay? That's another way of doing it. So SageMaker has been launched about a year ago now. It's been extremely popular, like Andy mentioned in the keynote. We have all kinds of customers. There isn't one specific type of customer. We have large enterprise customers like GE and Dow Jones and Thomson Reuters and Intuit. So people who have tons of enterprise data, customer data, and they just use machine learning across the whole company to solve all kinds of business problems. And we have also, obviously, web and web players like Hotels.com, Edmunds.com, Tinder. I wonder what they do with machine learning. No one's using it, so no one knows. Yeah, Realtor.com, et cetera, et cetera. And of course, these companies, they have mountains of user data and navigation data, click data, swipe data, et cetera, et cetera. And you can think of all kinds of applications where machine learning is important. Okay, and SageMaker helps all of them train and build, train, and deploy tens, hundreds of machine learning models at scale. Because again, what SageMaker really does for you is make that path from business question to model in production faster and simpler than it used to be. So you can innovate faster. You have much more agility in your machine learning process. Okay. If you want to know more about those stories, please go to the SageMaker service page, and you will see some use cases. And I'm sure we'll have plenty of SageMaker customers speaking at re:Invent this year. And the videos are being put online really quickly this year. So some of them might already be online. So let's talk about TensorFlow for a minute. So TensorFlow is an open source library. Who's already using it today? All right, quite a few people too. All right. So it's an open source library, and it's fair to say it's probably the most popular library for deep learning these days. The main API is in Python. There is some kind of support for other languages, but really most people use Python. It's quite easy to build all kinds of network architectures with TensorFlow. It has predefined APIs to build quickly fully connected networks, convolutional neural networks, LSTM networks, and all kinds of other architectures. So you can quickly, in just a few API calls, you can quickly stack those layers and build a network. The initial model for TensorFlow is based on symbolic execution. So symbolic execution it's a complex word for something that's not so complex. Symbolic execution means you first define the network, the execution graph, okay? So it's fully defined, and then you train it, okay? So you have those two distinct phases. Define the network, the graph, okay, then it's frozen, and then you train it, okay? And the fact that it's fully defined when you train allows you to run all kinds of optimizations for speed and memory, etc. You can run all those fancy graph optimization algos and get some speed up, okay? The problem with symbolic execution is the graph is frozen during training, right? It's really the downside to that. So this means you cannot change the network. You can't change the graph while training, okay? And for most applications, it's okay. But for some more advanced use cases, we actually want to maybe make the network deeper as training progresses, or wider, or we want to inspect. We want to stop training and look at weights and look at exactly what's going on. We literally want to debug that network just like we would debug code, right? And that's not possible with symbolic execution. So a few versions ago, TensorFlow introduced imperative execution. They also call it eager execution, which is really, it's the opposite. Here, you just run code, okay? Imperative code is what you do when you write Python, Java, C++, okay? So no one knew you were actually running imperative code, but that's what we're all doing. So now we can do the same thing for deep learning models, okay? So we can define and train and inspect the model and change the model during execution, okay? And this is available now as well, so you get those two modes. And last but not least, TensorFlow is complemented by a high-level API called Keras. Anybody using Keras? Okay, a few people. So Keras is a high-level API that sits on top of TensorFlow, Theano, and Apache MXNet now. And it's super user-friendly. It's my personal favorite, I have to say. Documentation is great. You can find tons of examples. They have a great blog, et cetera, et cetera. So it makes it really, really easy to build and experiment with deep learning models, okay? At the cost of performance, probably. But it's so easy to use that you'd be, it'd be a mistake not to try it. So actually, you probably heard Andy mention that there are over 80% of TensorFlow workloads are running on AWS. So there is a ton of TensorFlow workloads on AWS. So it's also our responsibility to make sure services like SageMaker and the deep learning AMI, et cetera, offer the best level of performance. And we spend quite a lot of time optimizing for that. So when we put the two together, what happens? So obviously, TensorFlow is a first-class citizen on SageMaker. We have a built-in container for TensorFlow, so you can just bring your own TensorFlow code, throw it at that container, and off you go. The container itself is open source, so you can build it. You can run it locally on your machine. You can customize it, push it back to Amazon, and train with it on SageMaker if you like. We support a bunch of TensorFlow versions, and we keep following the new ones. And we also have advanced features like optimized builds for GPU and CPU. So the version of TensorFlow that you run here is not the vanilla version. It's heavily optimized to make the most of our CPU instances and GPU instances. As I've mentioned, we support distributed training out of the box, zero setup. Okay, just say, hey, I want to train on 5 instances, and SageMaker takes care of everything automatically. We support pipe mode. Pipe mode is a way to stream huge data sets from S3 directly to your training instances, so there is no copying involved. So the benefit is you start training faster because you're not copying data to the training instances, and you can process infinitely large data sets. Okay, if you want to train on 1 petabyte, then fine. SageMaker will stream that petabyte to your training instances, and it'll take a bit of time, obviously, but you'll get to the end. Okay? You can use TensorBoard. TensorBoard is a visualization tool, that's hard to say. That shows you the training metrics, that shows you, you can visualize the graph, and it can run directly on the notebook instance. And so you just point your browser to port 6006, if I remember correctly, and then TensorBoard is available. And you can run Keras. I have another session where I show you how to build a custom container for Keras. Maybe I'll point to that at the end. And of course, you can do automatic model tuning, so you can use hyperparameter optimization as well. Okay. So I want to point out I did another session earlier this week. So it's AIM401. Okay. So it's the original one, and it's a technical deep dive on all those topics. Okay. So the session is going to be on YouTube any time now, any minute now. So if you're interested in all those advanced technical features, this is the video to watch. Okay. And there's a long demo of using Keras as well. Okay. So AIM401 is the one. Okay. So using Keras on SageMaker is also possible, like I said, and this is specifically important because this is what our friends did here, and they're going to talk about it. So the Keras layers, so the tf.keras API is available in SageMaker. It's part of the native TensorFlow API. If you want to use the Keras library itself, which brings many more APIs, then you need to build a custom container. Okay, it's not really difficult. You write a simple Docker file, build a container, push it to ECR, and then use it just like you would use any other job. If you're interested in this, this is the video I was referring to. It's the full process, full session on how to run Keras from scratch on SageMaker. Okay, building a custom container, etc. So before we dive into their crazy use case, I want to show you a simple example. And the simple example with TensorFlow is this. So this is a toy data set called MNIST. I'm sure you've seen this before. It's a bunch of tiny images representing handwritten digits. And of course, the name of the game is to classify those images into the 10 classes from 0 to 9. And this is actually the full code. Okay, there's not more than this. You could copy this and paste it and run it. Okay, so it's quite compact. So what do we do here? Import TensorFlow, grab the MNIST data set, which is already split into training and testing. We just normalize the pixel values. Okay, these are black and white images, so pixel values are 0 to 55. We want to normalize that to a floating point value between 0 and 1. And then we build a fully connected network. That's what Keras calls sequential. We flatten the image to have a flat vector as an input sample. And then we push that through a fully connected layer with 512 neurons, apply some dropout, which is a regularization technique to combat overfitting. And then we have the output layer with 10 neurons. Okay? And we compile the model, define the loss function, define the metrics, and train for 10 epochs, and then score. Okay? So that's all there is to it, right? I mean, this is a simple, fully connected network, and it gets probably to 90, I didn't run those numbers, but I would say probably 95 at least % accuracy on this task. Okay, so the power of deep learning is strong, right? Even with a few layers, you get a good accuracy. The last thing I want to mention is automatic model tuning, because this is an important part of the next use case. So automatic model tuning is about finding the right set of hyperparameters. Okay, so in the case of deep learning, what should the learning rate be, and how many layers do I want, and how wide should those layers be, how many neurons do I want in there, et cetera, et cetera. Okay, all kinds of parameters that are difficult to figure out. So the first way to do it is manual search, aka I know what I'm doing. Okay, well, it's a sad fact of life that none of us knows what they're doing. So that doesn't really work. Okay, you can try 100 combinations. You'll never know that you have the optimal one. So random search, aka spray and pray. That's my terminology for it. Just try to pick random sets of hyperparameters, hoping that if you train enough, right, if you train 100 times, 200 times with 200 different combinations, maybe you'll hit the right spot, okay? Not really scientific. The third way is grid search, aka X marks the spot. So it starts like just as random, okay? Pick maybe 10 or 100 combination of parameters, train, and then the assumption is there will be some area in there that is interesting, okay, where you have slightly higher accuracy. So you will zoom in on that part of the hyperparameter space and do it again, right? Zooming in on that hotspot that seems to deliver high accuracy models. So as a matter of fact, this is painfully slow because you can train literally hundreds and hundreds of models, so it's expensive. And it's not intuitive, but actually random search works better, which is very disappointing, right, from an intellectual perspective. And then the best option is to use HPO, which uses machine learning optimization. So it trains a couple of models, okay, looks at the results that it got from the parameters that it picked at random initially, and then it applies machine learning optimization in order to select the next bunch of parameters. So it's an iterative process where you train, let's say, 2 models, optimize the results, pick 2 more sets of parameters, and then based on those 4 data points, optimize again, and then on the 6, optimize again, on the 8, optimize again, et cetera, et cetera. And if you can't sleep tonight, you can read about Gaussian process regression and Bayesian optimization. I recommend it. It works very well if you can't sleep. And this is what SageMaker uses to quickly and efficiently deliver an optimal set of parameters. And it's so easy to set up. It would be a crime not to use it, right? And you don't need to know much about machine learning to use it. So I'll point you at the doc. You can figure it out in no time. But now it's time for Kevin to join us. So please give him a warm welcome, and Andrew as well, of course. Thank you. Thank you for joining us at reInvent.
Thanks.
And OK, hang on to your hats. This is going to be crazy, right?
Okay.
Good luck, guys.
Yeah, thank you, Julian. Good morning, everybody. So I'm Kevin Clifford, product manager at Advanced Microgrid Solutions, or AMS, and I'll be talking today about how we've used AWS and SageMaker to deliver a key business objective. So, and then I'll bring up Andrew to go through how we delivered on that. So first, a little bit about our company. We were founded in 2013. We're based in San Francisco, and we're a technology-agnostic energy platform and services company that maximizes wholesale energy market revenues for both behind-the-meter and in front-of-the-meter energy assets. Raise a hand if you know exactly what that means. OK, yeah, there's quite a bit of industry-specific terminology in there that I'll break down in just a moment. At a high level, we're the software layer that sits between physical energy assets and the various players in this space, so utilities, markets, retailers, as well as trading desks. So first, with energy markets, what is an energy market? Electricity is traded in regional wholesale markets where the operator is there to facilitate and oversee the sale and purchase of energy for a very specific geography. And one of their primary goals in doing so is to make sure that supply exactly equals demand at all points in time. Failing to do so disrupts the physical power grid, and then an outcome could be widespread power outages. So a key part of this is that at all times, demand varies widely through time as there's changes in behavior, changes in environmental factors like weather that are causing that to go up and down somewhat in a volatile fashion. And it makes this all that much more difficult for the operator to procure the exact right amount of supply to hit that changing target. Also, recently, there's been increases in volatility in the supply side as there's more renewables or intermittent generators that are brought onto the grid. So it makes kind of matching those two up in time very challenging. The supply side, if you look at the participant, their job is to come up with a bid, which is a pairing of price and quantity, and to decide how much they want to sell at a given point in time. The market operator then consumes all of those bids and then awards specific suppliers the right to generate. In turn, they're paid for this generation at what's known as the market clearing price. And so this is the price set by the marginal unit used to meet that demand target. Shifting over to energy technologies, so there's a wide range of generators out there. How they generate electricity differs. So you have thermal generation, gas-fired generation, you have renewables like wind and solar, you have hydroelectric dams, and you have a relatively new entrant, battery energy storage. So while they generate in very different ways, their cost to generate is also quite varied. So if you look at thermal generators, their cost is associated with the price of the gas they purchase to burn to then convert into electricity. On the other end of the spectrum, batteries, their cost to generate comes in the form of opportunity cost and weighing price arbitrage decisions and whether or not it's more advantageous to charge or to discharge energy. So when you're considering this kind of that end of the spectrum, it's important to have a very accurate price forecast to understand your opportunity cost, and more than just an accurate price forecast, an encapsulation of the uncertainty on that forecast. So you can weigh these decisions and make profitable decisions over time. So coming to our use case, we're looking to optimize market participation for battery energy storage in Australia's national energy market. So why Australia? Well, the Australian national energy market is one of the largest in the world, both in terms of volume and value. They serve 9 million customers in 5 eastern states. There's 200 terawatt hours traded, which totals to about $16.6 billion. The design of this market is that of a spot market where you can participate in 9 different avenues over a 24-hour span at a 5-minute interval. Only the next 5-minute interval, though, is binding. So you have every 5 minutes the opportunity to update your bid or to rebid with new information. So this makes this a very complex challenge, and when we think about batteries, it's perfect for this market design. A use-limited resource is perfect for creating and capturing value, but that's contingent upon accurate forecasts, one, to meet the requirements of the market, but also to understand your opportunity cost and then make the correct decision. So to go into some of the operational challenges of this use case, dependent on the market, is let's use one. So if we focus on the 4:05 to 4:10 window and say you want to bid for that time, that market actually doesn't, or you have to supply a bid to that market 90 seconds before then. So at 4 o'clock, 3 minutes and 30 seconds, you have to put that market, or that bid into the market operator's hands. But in order to make that bid, you need to know what's going on between the current window, 4 o'clock to 4:05. That information isn't delivered until 30 seconds in. So now you only have 180 seconds to carry out all the necessary tasks to deliver a bid that would ultimately get awarded by the market. That includes forecasting the price for the upcoming trading intervals, determining optimal asset dispatch, constructing a competitive market bid, presenting that to a user, and then delivering electronically to the market operator. If we look at all the later steps, you really only get about 50 seconds to do that price forecast. And you're going to have to do it again in 5 minutes. So you have all these different data streams that are quite volatile. They're changing in time. There's lots of different market participants who are entering and exiting the market as you go through longer periods. And so the trend is constantly changing. So it's an incredibly complex problem that requires a lot of targeted data science. And with that, I wish Andrew luck in developing and going through the solution to this complex challenge.
Thanks, Kevin. So just to repeat, my name is Andrew Martinez. I'm a data scientist at Advanced Microgrid Solutions. And before going into the solution that we ended up doing, I wanted to talk a little bit more about the motivation, give a little bit more background in terms of why we wanted to develop this forecasting model. And Kevin talked about it as well. But the one thing you need to know about the AIMO market, which is unique among other energy markets, is that they actually provide their own price forecast. And you'd think, okay, this is the market operator, though, so they should have the most information about what's going on in the system, both in terms of how everybody is bidding into the market, what is going on with the demand, as well as all the technological constraints, so the transmission lines, the power flows. So that price forecast should be relatively good. But there's one flaw in that price forecast, in that it's dependent on the bidding behavior of all the market participants. So the only bid that is binding is the bid that goes in for the next interval. And people can rebid every 5 minutes. So that means all of those future bids are maybe not representative of what they might bid when that time comes. But it means that we can learn from those bids and basically learn the bidding behavior of all the market participants and use that to come up with basically a better price forecast. So why did we go down the neural network route? So you can, again, because we've been talking about TensorFlow, we went down this deep learning route. So why did we do that? One is it's a complex market, right? So kind of like trying to understand and trying to forecast stock market prices, there's a lot of market dynamics. So there's not only seasonalities that you're trying to incorporate and common exogenous factors like weather, there's also a number of other feature sets such as the network outages and neighboring market conditions that you want to include in your price forecast and you intuitively know have influence on what the price forecast is going to be, but you don't know how much those features are important and what the correlation between those features are. And neural networks are very good at basically telling you which features are important and how they're related with each other. And the other thing is we wanted to build a model that could build with us, that could grow with us into the future. So as the market becomes more volatile, we wanted something that could dynamically pick up all of that new volatility. There's also a number of studies, I'm showing two here, that look at using deep learning techniques that show promise compared to statistical methods or other just machine learning, boosted tree sort of algorithms and methods. So we invested the time in going down the neural network route. So before getting into the model and the meat of what we built, just a quick overview of our architecture. So starting the process, so the majority of our input data is coming from a third-party database, an MS SQL database, and the third party is basically replicating the AIMO data, or the AIMO database in real time, so it's constantly updating. We have a job that goes out, pulls down all of the information, all the feature sets that we're interested in, does some pre-processing on it, and then pitches that to S3 so that it can be used by all the other AWS services relatively easily. Then when we're going to do our model training or model tuning, we are using SageMaker. And then we have, when we go to do the tuning job, we also have a connection to DynamoDB. So we're able, again, when you start to build a lot of these models, you want to store some of the metadata in it so that you know what version you're on, what code commit you're using, so that you can go back in time and say, okay, this forecast model at this particular time was using this input data, this particular model version, so you can replicate and you can kind of understand what's going on there. And so we made that connection. And then once the model has been trained and SageMaker has done its magic in determining what are the best hyperparameters to be using in our particular model, we're deploying it, again, using SageMaker, and then wrapping it using Lambda API Gateway and Route 53, basically as like a microservice. So there's a static API or a static address that's serving an API that we can basically hit saying, okay, give me the forecast at this particular time for this particular product. And it then in turn pulls in the data from the live data from the MSQL database, does some pre-processing on it, pitches that over to SageMaker, which does the inference, gets that inference back, does some post-processing on it again, and then display or sends the request back to us in a form that we're expecting. And then we're all doing, I don't know if you've used AWS Shoutouts before, but it's a nice little framework to do all of this orchestration and do this in Python. So now getting into the actual model and what we built. First, design considerations. So we knew that there's an existing market model, and we knew that we could learn existing market prices that are being presented by the market operator, and we knew we could learn deviations from that. But it wasn't just important for us to understand the point estimations of what those future prices could be, but also understand the uncertainty around those future prices. Because I'll get into this later as well, and it'll become more apparent as to why. And then lastly, and this comes into sort of our bidding and our bidding strategy, is we wanted to create a number of scenarios from that forecast so that we could run a stochastic optimization problem. And again, I'll talk about that in a little bit more detail So first step, start easy, right? This is the most basic model you can do. And we're calling this our benchmark model. So take the existing market forecast model, market forecast prices, and basically learn deviations from it. So again, 3-layer network, very simple. The input layer, you can think of it, it's the time series data. The output layer is now our predicted prices, and you're learning against what the actual prices were. So again, in Keras, this is very, very simple, 3-layer, and sort of showing the code there. So this gets at the first sort of modeling design consideration, but it doesn't get at the next piece, which is uncertainty. So how do we model uncertainty in this particular framework? So let's first figure out, okay, what's the output dimension that we need to have, right? So we want to have both the point estimations, but we also want to have forecasts for what the different possible quantiles could be, what their quantile forecasts could be. So let's start with just modifying the output layer. So again, we're adding a dimensionality to the output layer corresponding to the quantiles that we're trying to model. So now the output looks something like, okay, we're modeling 300 points in the future, as well as maybe 5 different quantiles. So it's a 300 by 5 output shape. So now we have the output dimensions correct, but now we need to tell the model how to actually predict what the quantiles are going to be. And this means that you have to modify your loss function. And you can do this by using what's called an asymmetric or a pinball loss function conditional to the quantile. So what this means is, let's run through an example. Let's say we're trying to capture the 90th quantile forecast, right? So the pinball loss function is basically skewing the error, or not skewing the error, skewing the loss. So let's say the error was 10. Because of this pinball loss function, how it works is that now the loss seen by that 10 error is 1. So you're basically skewing it to overprediction. And then on the other side, if there's a large negative error, so let's say the error was -10, the loss would be much greater. So again, it basically is learning to skew the results into an upper quantile and learning that higher quantile prediction. And again, so you can't do this in Keras, so you can write basically using TensorFlow, a custom loss function here, just using a maximization function and then a computed weighted loss function as well on top of that. So what does that give us? So walking through the graph, the blue line here represents the actual prices. So this is the price that actually materializes in the market. The green line, which is a little bit faint, but you can kind of see it, is what the market forecast predicted at time equals 0. And then the gray lines represent our forecast, our quantile forecast. So we're looking at 5 different quantiles, 10, 30, 50, 70, 90%. So there's a couple of things you can glean from this, and this is why it becomes very powerful and apparent why we were interested in doing this quantile forecast is, one, it tells us when we have a higher likelihood of the price not being volatile, right? So if the quantiles are closely clustered, then we know that the price is likely not going to be spiking during that time. Whereas if the quantiles became more separated, then there is a likelihood of this price spike occurring. So we can use that information in our bidding strategy to basically determine, okay, maybe we do want to reserve power so we can discharge later, or maybe we want to discharge now because we're certain that nothing else is going to occur in the future. So the last part of this is taking those quantile results is running and coming up with a number, and this is our last model design specification, is that we wanted to come up with scenarios that we could run through a stochastic optimization problem. And the thing here is that you could just randomly sample from that distribution, but the issue is that there's a covariance between both temporally as well as between the different products that you're trying to predict. So what we did was using the test data set, we basically derived both the temporal as well as the cross-product covariance terms. So what you're seeing in the graph here is essentially the covariance matrix for, I think this is the energy market product. And what you can see is that, starting, defined by the diagonal line, is that at a given point in time, t equals 0, it's highly correlated, and there's strong covariance with the t minus 1 as well as t plus 1. So, and when you are sampling from this distribution, you want to keep that relationship. And NumPy, I'm just going to point this out, NumPy has this really great feature to do a multivariate normal, so it allows you to basically input this covariance matrix and quickly sample from it. So this takes us a matter of seconds to come up with 10, 50 different realistic-looking stochastic scenarios, which we can then use in a stochastic optimization problem. So that was the benchmark model. So it meets our general requirements, so it improves upon the market forecast, and it was kind of surprising when we originally put this model in place and saw that it was, well, the existing model is pretty bad, their existing prices are pretty bad, but we got pretty good results with this simple model. The limitations were, as we started to add more and more features to it, it became prone to overfitting. So the next steps were to develop a more robust model that was less dependent on regularization methods, and sort of use intuition to feature and target dependencies to reduce model connectivity. So that led us into convolutional neural networks. So I don't know if most of you are familiar, but convolutional neural networks are primarily used, or they use in time series classification, but primarily in image recognition, right? Because they're good at recognizing particular patterns in a spatial set. But that pattern recognition can also be used in time series data. And in particular, with dilated convolutional neural networks, you get this nice property that you can basically model a large receptive field. So the receptive field, meaning the connection of your input layer to a single output node, grows exponentially with the number of layers and your dilation rate. So this allows you to have memory. So similar to an LSTM model, you have memory of what is going on in the past, or in the A causal scenario, also in the future. So you have those connections. And because it's a convolutional network, all of the weights are shared, right? So you have less learned parameters, which helps reduce overfitting because you have less parameters to learn. So as an example, just running through this, the top one is the A causal scenario with 3 layers, a kernel size of 3, and a dilation rate of 3. So you can sort of see how the inputs are related to the particular output. And then the causal scenario is, instead of looking and including points in the future, you're just including points in the past. And then typically these convolutional stacks, or these convolutional layers, are typically stacked with residual connections, and that's done primarily for to facilitate better learning. And there's some papers on exactly why. Okay, so as we were building out the model, so we started with this benchmark model, and then we went down this convolutional route. As we started building into the complexity, there became very apparent to us, and it becomes apparent to most people who are doing these sort of deep learning models, is that the number of hyperparameters that exist, it just kind of explodes. You're just like, okay, how many layers should I build? I don't know, let's parameterize that. What should the filter size be? I don't know, let's parameterize that. So we ended up basically creating this very parameterized model such that instead of basically relying on us to create and define those hyperparameter points, we're leaving that up to the machine. So we're leaving that up to, in this case, SageMaker to do its magic and do its Bayesian optimization. So again, these are the parameters, they're the hyperparameters that we chose. And so looking at our hyperparameter tuning jobs, so on the graph that I'm showing here, The x-axis is all of the different parameters that we are, that are all of our hyperparameters. And then the y-axis is the absolute value of those. So it's a little skewed because some of the value, like some of the hyperparameters are categorical or they're ratios. So sort of ignore the height. But the thing that you can gather from this particular graph is that it's fairly non-intuitive. There doesn't seem to be some particular path that gives you the best results. And the way to read this is that each one of those sort of lines represents one of our training jobs. And then the more fuchsia and thicker, I don't know why we did that, but are the better job. It has lower loss associated with it. So this is representing the 36 lines for the 36 jobs. We ran these, 3 in parallel. Each job takes about 2 hours to train, so that's 72 training hours. And we were able to get away with using a relatively small instance. Actually, I think the smallest machine learning instance, GPU instance. So this, if you kind of do the cost analysis here, that costed us about $100 to do, right? And the astonishing part is that we saw a 20% difference between the lowest loss and the highest loss between these jobs. So when, that might not seem like a lot, but when you're talking about using this to then inform a multi-million-dollar asset what to do, it pays for itself relatively quickly. It's a pretty low sales pitch to the people who actually have to pay the AWS bill. So, so the accuracy, so getting into how well we did. So again, following common modeling validation practices, we split the data up into 3 different chronologically separated groups: the training, test, the training, validation, and test set. So validation is where you're doing all of your hyperparameter tuning, and then your test set is independent from all of that and where you're doing your final comparison. So for this particular case study, looking at the South Australian energy prices with the 24-hour look-ahead period, we are seeing a 68% reduction in the mean absolute error against the existing market forecast. And this is a little skewed because the existing market forecast is pretty bad and also predicts a lot more like price spikes, so it kind of skews that particular metric. So a better metric to use would be the median absolute error, which doesn't takes out some of those outliers, and where we're still seeing a 24% reduction. So this by itself is a great win for us and showed us that building out this model, we can do a lot better than the existing price, and we can now, and especially when we're just looking at the point estimates here, but when you also include the quantile forecast, it gives us a lot more information that we can use to inform our bidding strategy. So key takeaways. So without prior experience using deep learning tools, we deployed the benchmark model, that simple 3-layer network, using SageMaker and TensorFlow within a matter of weeks. Then we basically continued to build on that over the next couple of months to basically, in looking at literature, come up with and build to basically a state-of-the-art temporally dilated convolutional neural network. And it meet all of our modeling criteria, or our acceptance criteria, in that it provided us both with the point forecast as well as the quantile forecast, as well, and realistic scenarios that we could use in stochastic optimization. So recommendations, start simple. Again, there's examples that you can basically pull from, and it can get you up and running very quickly. Keras, again, is a powerful high-level library that allows you to do this, again, very quickly, and it's very approachable. And then lastly, as you start to build complexity into your models, start to parameterize, right? Try to take the art out of deep learning architecture and let tuning sort of discover the best solutions for you. Again, before I sort of pass this back over and sort of open the floor for questions, I wanted to give a big shout out to Corey Noon, who's actually the first author on a lot of this work, and this is primarily his brainchild, but he's on vacation, on a well-deserved vacation right now in Thailand, so you're stuck with me instead of him stalking. And then shameless plug, We are hiring data scientists and software developers, so if you are intelligent, engaged, and want to work for a clean tech startup in San Francisco, please look us up and reach out. Thank you. Oh, some resources.
Right. Thanks. So, I told you, right? I told you, these guys are awesome. This is really, some of those slides probably can keep you busy for a few weeks, right? Trying to get to the, yeah? I know they're still keeping me busy, but this is awesome. This is exactly the kind of content that we want to see. It's a deep dive session, so again, congratulations. So just a few resources to get you started. TensorFlow and Keras have extensive websites, tutorials, documentation. You can get started. If you're really, really new to this, I would really recommend you start with Keras, right, which is really the approachable one, as you say, and within an hour or two, you're already running stuff and learning, right? So this is really the entry point I recommend. Obviously, the notebook samples, I cannot agree more. These are a great resource to get you started with SageMaker and see how you can scale and tune your jobs really easily. The SDK that I mentioned as well is on GitHub. And if you like this stuff, if you want to read more about it, I have a blog on Medium where I post a lot of articles and tutorials about deep learning and SageMaker, and that's probably more interesting content for you. So please don't forget to rate the session in the app. And I want to thank you again for showing up on Friday morning, closing reInvent in style with us, hopefully. And I want to thank again Andrew and Kevin for showing up and delivering this great use case. Thank you very much.